Welcome, this is Coach Dorf. Today we're going to continue our discussion about limits, and we're going to talk about how to evaluate specific limits. So our goal in our discussion today is to find the value of limits of specific functions. Let's look at a specific example here. Suppose we had the limit as x goes to 2 of 3x minus 1. We're going to use a technique called direct substitution. And in that technique, what we do is we take the value, in this case, x equals 2. Where do we get that? Well, x is going to 2, so we're going to let x equal 2. And by direct substitution, we mean then that we substitute in that value x equals 2 here in for x. And when we do that, then we get 3 times 2 minus 1, or 6 minus 1, and we get 5. And that's the value of the limit. Really pretty straightforward right there. Now, of course, you're going to be thinking all the problems aren't going to be that easy. And that's right. They're going to get more difficult. And that's where we're going to continue our discussion now, is what happens when you do that and you can't see what the answer is. What do you have to do? You have to do more work. And we're going to talk about what that extra work is. So let's look at the next example here. That's a more difficult. So I have the limit as x goes to 2 of x squared minus 4 over x squared minus x minus 2. So I'm going to label my function to be f of x. So f of x is going to equal x squared minus 4 over x squared minus x minus 2. And I want to look at f of 2. Again, I'm picking 2 because that's what my limit is. That's x is going to 2. So when I do that now, I put 2 in for x. So in the numerator, I have 2 squared minus 4. In the denominator, I have 2 squared minus 2 minus 2. And when I simplify that, I get 0 over 0. That's not my answer. 0 over 0 is what's known as an indeterminate form. Oops, let me spell that correctly. Try that again. It's an indeterminate form. What that means, it's not determined. The suffix, the prefix in means not, so it's a not. You cannot determine what the answer is from this. So we have to do more work. And what is that more work that we're going to do? We're going to factor. So write my problem down. X is going to 2 of x squared minus 4 over x squared minus x minus 2. And then when I factor the numerator, I get x plus 2 times x minus 2. And when I factor the denominator, I get x plus 1 times x minus 2. Notice there's an x minus 2 on the top and an x minus 2 on the bottom. I can cancel those out, and then I get my limit as x goes to 2, and I rewrite it. I've got x plus 2 over x plus 1. And now when I do direct substitution, I get 2 plus 2 in the numerator, 2 plus 1 in the denominator, and I get an answer of 4/3. And that is my correct final answer. Now, why does this work? Why can I cancel out the x minus 2 in the top and the x minus 2 in the bottom? Remember last time in our discussion about limits, it didn't matter what the value of the function was exactly at value x equals 2, because I have my limit here, x is going to 2, so the value of the function at 2 doesn't matter. So I can cancel those out from the top and the bottom, all right? And when I do that, then it makes the problem simpler. I'm able to go from the indeterminate form to a determinate form where I can actually get the correct answer. Now let's do a variation on the problem, this problem. Suppose I just change this one problem, and I now write that we have the limit as x is going to -1 from the right of x squared minus 4 over x squared minus x minus 2. Now notice here that I'm doing a one-sided limit, this little plus here. Remember what that means is I'm taking numbers a little bit larger than -1. I'm approaching -1 from the right side. This is called a right-hand limit. So if I do my direct substitution here, so I've got my function again, f of x is x squared minus 4 over x squared minus x minus 2. And I'm going to look at from -1. Now, even though I have a one-sided limit, I can go ahead and do a direct substitution at that x value. So in this case, it's -1, again, because of this, got that. And when I do a direct substitution, what happens? Well, I get -1 squared minus 4 over negative 1 squared minus a negative 1 minus 2. And then I get 1 minus 4 over 1 plus 1 minus 2. And that's going to give me negative 3 over 0. Is this an indeterminate form? No, it's not. It's not 0 over 0. It's a non-zero number over 0. From last time, then, we discussed that in this case, my limit has been reduced to 3 possible answers. It could either be positive infinity, negative infinity, or does not exist. And how do I determine which one it is? Well, I need to look at the sign of my function, my numerator, my denominator of the function. So if it turns out that the top is positive and the bottom is positive, then I get a positive value. And so I'm going to get positive infinity. So I just need to figure out what the sign is for my function. All right. So, and to do that, I'm approaching negative 1 from the right. So it's the numbers that are a little bit larger than negative 1. So let's take 0. So if I just look at f of 0, then I'm going to get 0 minus 4 over 0 minus 0 minus 2. That's going to give me negative 4 over negative 2, which it doesn't matter what the number is, but that's going to be a positive number. And so that means my answer here is positive infinity. This doesn't really matter. What matters is the sign here. It's a positive number. So again, see the difference between the previous problem where we got 0 over 0 when we did direct substitution, and this problem where we got a non-zero number over 0. All right, so then let's look at another example of using direct substitution. All right, so I'm going to call this example, how many examples have I done already? I've done 2, so I'm going to start labeling these. We'll call this example number 3. And we're going to have the limit as x goes to 2 again, but a different function, 1/2 minus 1 over x, all over x minus 2. All right, so we try direct substitution. So again, my function is going to be 1/2 minus 1 over x, all over x minus 2. And I'm going to look at f of 2 because x is approaching 2. Just to signify that tells me that this is a 2 here. And when I do that, I get 1/2 minus 1/2 in the numerator and 2 minus 2, which is going to give me 0 over 0. And this is my indeterminate form. So I don't know what the answer is yet. So what I need to do is I need to do more work. Now, can I factor something out of the top and the bottom? Well, I can, but I can't see how to do that yet. So I'm going to do some more work before I factor. And what is that more work? Well, I want to simplify what's in the numerator of this function here. I have a fraction minus a fraction in there. I have 1/2 minus 1 over x. Let's simplify that. So how do I simplify that numerator part? Well, I need to get a common denominator. My common denominator is going to be 1 over 2x because I have a 1/2 and I have a 1 over x. So I want 1 over 2x. So if I start with 1/2, I need to multiply the denominator by x in order to get 2x in the denominator. And if I multiply the denominator by x, I need to also multiply the numerator by x. So I'm going to take 1/2 multiplied by x over x. And then I have 1 over x here, means I need to multiply the denominator by 2. So I'm going to multiply the top by 2 so that I keep it equal like that. All right, now we'll do the next step. When I do those multiplication of those fractions, in the numerator, the first one I get x over 2x. In the second fraction, I get 2. And I can put that as 2 times x because it doesn't matter whether, since multiplication in the denominator there, I can have x times 2 or 2 times x. So I'm just going to write as 2x. And then I have this in the denominator there. So now I have the limit as x goes to 2. In the numerator, I can add those together to get x, or subtract them. I get x minus 2 over 2x. And that's all over x minus 2. So now I have a fraction over the x minus 2. I can think of the numerator that x minus 2 is also a fraction by putting a 1 in the denominator. And when I'm dividing fractions, that's equivalent to multiplying by the reciprocal of what's in the very bottom. That means I've got x minus 2 over 2x. So I'm going to multiply by the reciprocal. That means I flip the numerator and denominator of this part. I flip that. So I'm now going to get 1 over x minus 2. All right. So you can think of this, some of you don't need to do this next step, but you could think of this as x minus 2 times 1 in the numerator, and then in the denominator, I've got 2x times x minus 2. And now I see that I can cancel out something from the top and from the bottom. All right, there's an x minus 2 in the top and an x minus 2 in the bottom. What does that leave me in the top? It doesn't leave me with nothing. It leaves me with a 1. And so then I have the limit as x minus 2 of x goes to 2 of 1 over 2x. And now I do direct substitution and I get 1 over 4, and that's my correct answer, right? Now, let's do another example. So this is example, let's say I think number 4. Yep, example number 4 here. Do the limit as t goes to 7. So it doesn't matter what the variable is. So I'm going to do a t here. Let me make that not so large. Square root of t plus 2 minus 3 over t minus 7. Okay. By direct substitution, then I get that f of 7. So when I plug 7 in, substitute 7 into the function there, I'm going to get the square root of 7 plus 2 minus 3 over 7 minus 7. And that's going to then equal square root of 9 minus 3 over 7 minus 7, which is going to give me 0 over 0. So again, indeterminate form. And so we need to do more work. All right. So can I factor here? Well, you could, but I don't see how to do that yet. It's possible to factor that, but it's just too complicated. So I want to, just like in the previous problem, we want to do some more work to put it in a form so that we can factor. And what is that work I need to do in order to simplify it so that I can find something to factor? Well, we're going to multiply. I've got a square root in the top. I've got two terms in the numerator here. I've got a square root minus a number 3. So I'm going to multiply the top by a thing that's often called the conjugate of the top. And what that means is I take that same square root, and so it's going to be the square root of t plus 2, and I'm going to take that 3, but I'm going to change the sign between them. So this one is a minus and this one is a plus. So you change the sign. Now, if I do that to the top, anytime I have fractions and I do something to one part of the fraction, I have to do it to the other part. So I have to multiply the bottom by the same thing. That square root of t plus 2 all plus 3. Now, you may be thinking, this does not look easier. At this point, it does look more complicated, but now things will become easier as we work through here. All right, so I need to multiply in the numerator these terms together. So first I get the square root multiplied by each other. So that's going to give me the square root of t plus 2. And I'm multiplying them together, so I have 2 of them, so that's squared. All right. Then I'm going to go ahead and multiply t plus 2, the outside ones, times a plus 3 to get me 3 square root of t plus 2. All right, I don't know if these colors are helping or not. Then I'm going to do a t plus 2 square root times the minus 3. So it's going to give me minus 3 square root of t plus 2. And then the last one I'm going to do is minus 3 times a plus 3. So that's going to give me minus 9. And in the denominator, I'm just going to keep everything the same. I'm not going to multiply it through. You might want to do that, but it's going to be easier if I don't do that. Now let's simplify what's on the top. When I take that purple part and I've got the square root of t plus 2 squared, that's just going to then end up to be t plus 2. Square root of t plus 2 squared is just t plus 2. And then notice that I've got the blue part and the orange part, and they cancel each other out. One is a plus 3 square root of t plus 2, and the other is minus a 3 square root of 2. Those cancel out. And then I'm just left with a minus 9. The reason that always should happen, that those two middle terms cancel out, the plus 3 square root of t plus 2 minus the 3 square root of t plus 2, those cancel out. They cancel out because we picked the problem to multiply by the conjugate. If I choose the right conjugate, the middle terms will always cancel out. And I choose the right conjugate by doing, whenever I have that square root there, I just change the sign from, in this case, it was from a minus 3 to a plus 3. All right. And then in the denominator, I don't do anything, just rewrite it down. And then I notice that my numerator, it simplifies to be a t minus 7. And in the bottom, I have a t minus 7. And I have then times the square root of t plus 2 plus 3. And lo and behold, now I have the same thing in the top and the bottom, and I can cancel those out. Leaves me a plus a 1 in the numerator. And so now I have the limit as t goes to 7 of 1 over the square root of t plus 2 is 3. And when I do the direct substitution now, I get 1 over square root of 7 plus 2 plus 3, which is going to be 1 over the square root of 9 plus 3, which is going to be 1 over 1 plus 1 over 3 plus 3, which is 1/6. Get the answer. All right. Now, notice a couple things here. Some of you may wanted to, at early on, to have multiplied these together. We didn't want to do that because we saw eventually then, as we got down to here, because we didn't multiply them together, we were able to cancel out the t minus 7 in the top and the bottom. If we had multiplied the terms together up here earlier, it would have been harder to see that, all right? I also want to point out one other thing in all these problems. What is being canceled out in the top and the bottom? What is the term that is always appearing in the top and the bottom? Well, in this case, it was a t minus 7. In the previous case here, previous problem, it was the x minus 2. Notice this is related to what my limit is going to. In this case, my limit is x is going to 2. All right, that's the same thing as saying x minus 2 equals 0. That's what that x minus 2 going to 0 equaling 0 is why I get 0 over 0 in the original part where I had this indeterminate form. Likewise, down here in this previous example, I had my t going to 7. So that's t minus 7 equaling 0. That's also the t minus 7 that we canceled out. That's the 0 over 0 we cancel out. That will always happen in these problems. Whatever your limit, your x is going to, or your t is going to, you write that as t minus that number. That's what you should get to cancel out in the top and the bottom when you work on simplifying these types of problems here. All right, let's look at some limit problems where we have some absolute values here. So limits with absolute values. This raises the difficulty level a little bit of the problem, but we can still do this. All right, so let's say we have the limit as x goes to 1 from the right of x squared minus 1 over the absolute value of x minus 1. So again, this is a right-hand limit problem, right-hand limit, meaning that I'm taking numbers a little bit larger than 1 here. All right, if I do my direct substitution here, so if I have my f of x equals x squared minus 1 over the absolute value of x minus 1, and I did my direct substitution here, putting in 1, again, from here, where we get the 1. When I do that, I get 0 over 0, so indeterminate form. And so I need to do some work. Now, you may say, well, if I look at that limit, I can factor the top, which is right. I can factor it. And when I do that, I have x plus 1 over x minus 1 all over the absolute value of x minus 1. Oh, let me take a little commercial break here. Notice that when I've been doing these problems here, I've been writing the limit term each time. In other words, I've got the limit here, I've got the limit here, and in the previous problems, I was always writing the limit, 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 limit. That is the correct way to do this. Don't not write that. To me, it's like punctuation in a sentence, all right? If you leave off, if you're writing a narrative sentence, you leave off commas and periods and you don't capitalize things like that, it's hard to understand what the person is writing, and it doesn't make sense grammatically often. The same thing is true here with these limits. It doesn't make sense mathematically if you stop writing that limit there, right? So keep writing that limit. All right. Otherwise, you might miss, it's not mathematically correct. And on a homework or an exam, you could miss some points for that. All right. Now, going back to, that was the end of the commercial break. Sorry. So now going back here, let's see here. Can I now cancel out something on the top and the bottom? Well, I almost can. I've got this x minus 1 here, but I've got this absolute value of x minus 1. I can't just cancel those out because I have that absolute value. So what we're going to have to do here is get rid of that absolute value. So we want to get rid of absolute value around the denominator there. And what we're going to do now is we're going to use the fact that we have a right-hand limit. So we have x approaching 1 from the right, which means so x is going to be larger than 1. We can't, we're approaching x from the right, so it means numbers that are a little bit larger than 1. So x is always going to be larger than 1. Well, if x is larger than 1, that means x minus 1 is larger than 0, right? If I take this here, if I subtract 1 from both sides, that's going to give me x minus 1 on the left side, and if I subtract it on the right side, I'm going to get 0. So x minus 1 is 0. All right. So the fact that since x minus 1 is larger than 0, that means the absolute value of x minus 1 is going to be equal to x minus 1 because this is greater than 0 and this has to be greater. This has to be greater than 0, right? Because x minus 1 is greater than 0, then the absolute value of x minus 1 is also going to be greater than 0. So I can say the absolute value of x minus 1 equals x minus 1. If you have a hard time seeing that, let's just take a number. What's a number greater than 1? 2. Here's a number greater than 1. If I do absolute value of 2 minus 1, so let's just do a little check here. Suppose x equals 2. So the absolute value of x minus 1 then would be absolute value of 2 minus 1, which would be 1, absolute value of 1, which is 1. And 2 minus 1 without, x minus 1 without the absolute value would be 2 minus 1, which equals 1. All right, these are the same. And that's not a proof that this works, but that should convince you that this is right. So the fact that x minus 1 is greater than 0, I can drop the absolute value. All right, so again, we have the absolute value of x minus 1 in this case is equal to that since x is approaching 1 from the right, which means that x is greater than 1. So then if I go back to my problem, the limit as x is approaching 1 from the right we had x plus 1 over x minus 1, absolute value of x minus 1, absolute value. Now I can drop the absolute value here in the denominator then to get this. And I can do that. This goes to this because, as we just showed, this is true. So then I'll use a different color than red there. I can cancel these out, and then I have my limit as x goes to 1 from the right of x plus 1 over 1. And by direct substitution now, then I get 1 plus 1 over 1, which gives me 2. All right, let's consider a variation of this. Consider the limit as x goes to 1 from the left. Same problem, but I'm doing from the left this time. So we already showed that the numerator factors, and we get this. Last time we were able, in the previous example, we were doing it from the right, and we were able to drop the absolute value. Does the same thing work here? So we have that x is approaching 1 from the left here. So what does that mean? This means x is approaching 1 from numbers that are a little less than 1. So x is now less than 1. And if I subtract 1 from both sides here, that means x minus 1 is less than 0. So x minus 1 is a negative number. So what's the absolute value of x minus 1? Is that going to equal x minus 1? No, it's not. This is positive, but this is negative. So they're not equal to each other. So what I have to do, so no one tells me later that I made a mistake there. That's not true to say that they're equal to each other. Instead, what we get is that the absolute value of x minus 1 is going to equal the opposite of x minus 1. All right, because now this is a positive number, and this whole thing is the negative or the opposite of a negative number, which is a positive number. So we have now two positive numbers here. It can be confusing here because we may think that because we have this negative there, that means that this whole thing is negative, but it's not. It's the opposite of a negative number. It's a positive number, or you could think of it as two negatives. Negative times a negative gives me a positive number. So in this case, again, so summary, since x is approaching 1 from the left, x minus 1 is less than 0, and so the absolute value of x minus 1 is equal to the opposite of x minus 1. So then now my limit as x goes to 1 from the left, we had up here earlier, x plus 1 times x minus 1 all over the absolute value. Now I can write that as the limit as x is going to 1 from the left of x plus 1, x minus 1 over the opposite of x minus 1. And I've gotten rid of the absolute value. And now I can cancel these out because they're the same. And then I have the limit as x goes to 1 from the left of x plus 1 over negative 1. And now I can do direct substitution, and I get 1 plus 1 over negative 1, and I get negative 2. See how those two are different. When I earlier here, when I looked at this case where when I'm approaching it from the right, we got 2. When I approach it from the left here, we got minus 2. And let me just as a review, you should be able to answer this now. What's the limit as x approaches 1, not from the left or the right, but just 1, of x squared minus 1 over absolute value of this? The answer is does not exist. And the reason is because the right-hand limit, as we showed it above, equal 2, and the left-hand limit equals negative 2. And last time I checked, 2 and negative 2 are not equal. And whenever the right-hand limit and the left-hand limit are not equal, that means the limit from both sides, so in this case, x going to 1, does not exist. Let's see. Let me do another type of one here. Let's get back to black. All right. And looking at my problems here, let's suppose now we have the following. I'm going to let f of x be a piecewise function. So my piecewise function, I've got several pieces here. I've got x, x squared, and 5 minus x. So x is what the function is going to equal if x is less than 0. And x squared is going to be what the function equals if x is between 0 and 2, where it could equal 0 or it could equal 2. And the last one is going to be if x is strictly greater than 2. So what are the following? Let's say I'm going to do the limit as x goes to 2 from the right. So what I have to do here, so I'm doing a piecewise function here, going from 2 to the right, so numbers a little bit larger than 2. Which happens here? What value, when is x larger than 2? Well, that happens here. X is larger than 2 gives me this third case here. So this is going to be the same thing as the limit as x is going to 2 of 5 minus x. And now I can do the direct substitution, and I get 5 minus 2, and I get 3 as the answer here. Again, it doesn't matter. When I do the direct substitution, I can put in 2, even though I'm doing a right-hand limit there. Now, I'm sure a lot of you would say, well, what about if I do the limit as x approaches 2 from the left? Do I get the same answer? Well, going to our function here, when do we have x? So if I'm going to a left-hand limit, that means x is a little bit less than 2. What case do we have here? That's this case, middle one. Those are the values when x is less than 2, a little bit less than 2. And so this one then is going to be the limit as x is going 2 from the left of x squared. And now when I do my direct substitution, I'm going to get 2 squared, and I'm going to get 4. All right. And then just as a review, what's the limit as x goes to 2 of this one? All right. Well, it's going to be does not exist. And that's because these, meaning this one and this one, are not equal. If they were equal, then what would be the value for part C? It would be the equal value that both the right-hand and left-hand limit equals. All right, the last thing I want to talk about in this presentation is a thing called the squeeze theorem. Now, sometimes you won't have a specific function, or you won't have a specific way to determine a function, but you're given some information about the function, and specifically you're given information that the function is between two different types of functions. I call this the squeeze theorem. People call it the squeeze theorem. Some people call it the sandwich theorem. You could think of it as having 2 pieces of bread. So let's say I have a piece of bread here and a piece of bread here, and I put jam on it. And when I put the top onto that and I push them together, the jelly or the jam gets squeezed in between them. That's what's happening here. The function we're trying to find the limit of is like the jam. And I've got a function underneath it, which represents the piece of bread underneath it. And I have a function above it, which represents the piece of bread on top of it. And I put the breads together, and then the function I have is the jam in the middle. It gets squeezed in between the two. All right. That allows us then to figure out the value of the function, even if we don't know what the function is. All right, let me give you an example. I think that will be the easiest way to see this. All right, suppose we have this function here, negative x squared plus 4x minus 1 is less than or equal to a function f of x, and that is less than or equal to a function x squared minus 4x plus 7. We're supposed to find the limit as x goes to 2 of f of x. A new nib on my pen here. So notice here that sorry, got a back button here, but I don't. Notice here that my f of x in blue is always between these two functions. Let me go ahead and sketch the graph of this. 1, 2, 3, 4. So here's my x-axis, here's my y-axis, and I'm going to have my, let's see, I'll pick some colors here. I'm going to pick my function x squared minus 4x plus 7. And if I'm going to graph that, and it looks like this. Now I'm going to do my function negative x squared plus 4x minus 1, and that's going to be a function, and it's going to look like this. I'm going to take my blue function of x, and I don't know what it is, but I always know that it's between these values here. So you see the blue part is always between the orange and the green part. And what happens when I get to x equals 2 is that I notice the limit as x goes to 2 of the top function by direct substitution. That's going to be 2 squared minus 4 times 2 plus 7, which is going to be 4 minus 8 plus 7, which would be 3. And the limit as x goes to 2 of the bottom function, when I do that one, I'm going to get negative. When I did 2 squared plus 4 times 2 minus 1, it's going to give me negative 4 plus 8 minus 1 is going to equal 3 also. This and this are the same. And that's demonstrated by this fact here. There's that 3. Well, if my f of x is between those two, the only way it can be between 3 and 3 is if it's equal to 3. So since f of x is squeezed, the word, is it squeezed? Squeezed between the limit of the top function, which equals 3, and the limit bottom function, which also equals 3 at that point, then f of x, the limit of f of x there, has to also equal 3. All right, let me just say that one more time. If I know my function, my original function is between two functions, and I'm supposed to find the limit of my unknown function f of x at some point, I can go ahead and evaluate my top function at that point, in this case x equals 2, which we did right here. We evaluated it right here, and then I can evaluate the function here. And if those two limit values are the same, then my function has to have that same value. And some of you may ask, well, what if those two values aren't the same? If they're not the same, then we can't say anything, all right? But my experience is if they're going to give you a problem like this, it's going to be the same, and that's what you're going to have to use. All right, hope that helps you with the homework from this section and help you understand the ideas. Have a good day.